good morning, muy buenos días, dzień dobry. And thank you, of course, to Professor Hormis and to Alejandro for having me today. I've been listening also to Pere and Jordi and thinking a little bit about, how can I make this relevant for you guys? Maybe a short word about myself before anything else. So my name is Harry Zimmerke. I did my PhD in physics at a synchrotron in Germany, in Bonn, under Professor Hormis, actually, in the area of microsystems technology. I've been working in chemical industry now for 22, 23 years. And it's a fairly simple to summarize career. I was 5 years in research and development, 5 years in IT, 5 years in business and marketing, and now I've been 6 years in strategy. So I am working at corporate development, which is the strategy department of Lanxess. And I was thinking a little bit, how can I build an arc? Lanxess does not work with the synchrotron right now, but how can I build an arc that is hopefully interesting for this round today? And what I was thinking, maybe we can go to the next, I can go to the next slide. Hey, it works. Before I start, so chemical industry, why is that? Oh, is this loud? This is a bit loud, right? Why is chemical industry in Europe important? Because in the 18th and 19th century, they started solving big problems. So at the end of the day, and that's something I want to make here very clear, you get money. Money is a metric for how well you solve an important problem. So, and it's two components. Is this problem important? Then you get money. And if you solve that problem very well, then you get even more money. So let's keep that in the back of our minds. Chemical industry started, making pigments, as some of us know, making agricultural goods, solving hunger problems. That was kind of the situation at the early 20th century with BASF. And in that time, a lot of huge chemical conglomerates appeared. So it was like BASF, Hoechst, all of these. And then what happened? Economics happened. So more and more over the past 20 years, companies have been forced to focus on their so-called core business. So it's not like I do everything from cement to agriculture. So it's like you need to be focusing on one thing. So all these big, the BASF is the only one that's still left, but most of these big chemical companies have broke down. We ourselves are a spin-off from Bayer. So Bayer had originally Bayer Polymers, Bayer Chemicals, Bayer Crop Science, Bayer Healthcare, and they basically decided, we have a bad bank, chemicals, there's no margin in that, polymers, so let's put that all into Lanxess, let's, sort of get rid of that bad bank. That was 2004. And what then happened is basically, everybody got told, so what? We are the leftovers, we are the bad bank, let's show Bayer what we are made of. And everybody sort of pulled up their shirt sleeves and started really working very hard. And 10 years after, you would have said Lanxess is really the poster child of how a chemical company can turn around. So that went fairly well. I think that's what I want to say about this one. Maybe I can go to the next slide. So what does Lanxess do? I mean, as a German chemical company, of course, we have a whole bunch of sites in Germany still. But we have become more and more an international company. Over the past years, we've been carrying out a series of acquisitions. We bought Chemtura. We bought a series of material protection companies. So we have diversified and internationalized quite well. So what do? We have 4 major segments, doing chemical intermediates, doing specialty additives or lubricants or for plastics, a lot of consumer protection and stuff really like water purification. I mean, water is extremely important. There is a billion people on Earth do not have regular access to drinking water. I mean, that's a fairly violent number. So we try to solve that one. We do also iron oxide, so that's something we also apply for coloring concretes and things like that. We have a polyurethane systems, so elastomers. If you have ever used inline skates, rollerblades, then probably it's our material in there. We do a lot of insect repellents, so saltidine, icaridine, that kind of thing. So keeping, I was bitten by mosquitoes this night in the hotel. I don't know who else, but so if I had brought that, I would have avoided it. And flame retardants, of course, additives. We do have also a bit of plastics, but that is currently leaving the company in a joint venture. So we are very much committed, and this is something that is really a hard matter for the CEO that we have, to really addressing these societal goals. He has 4 children, and at one moment in one of these town halls, he got up and said, you know what, I have 4 children. I do not want them to ask me in 20 years, the world was on fire, what did you do? So he said, chemical industry is perceived as being the problem, but we are going to become part of the solution. So really, we are coming back here to the point I was making at the very beginning. Let's look at those big unsolved problems and solve them, and then we will automatically make money. Yeah, so of course, we are aiming to become climate neutral by 2040. And again, we're talking about assets that produce hundreds of thousands of tons. I mean, I don't know if anybody has a picture of what 100,000 tons looks like. I mean, a ton is a cubic meter, so that's already one part of it. And then so we make hundreds of thousands of tons of materials in assets that are fairly old. I mean, some of our assets or production facilities are 100 years old. And they were all designed for efficiency, for high yield, for making products with very high quality, with very high reproducibility, but never for low CO2. So we're going to have to go under a huge transformation for that. Then reducing water consumption, of course, increasing the safety for employees, increasing, that's maybe a German problem only, increasing the proportion of women in management. We are not always very good at that. I'm going to assume that I only have like 6 minutes. Oh, okay, good. Okay, well, thank you. Good. Climate neutral. That means producing hundreds of thousands of tons of different materials and emitting 0 tons of CO2. I'm going to let that work through your... That's an incredibly tall order. So a few of the things were fairly easy. So cutting down at the beginning, sort of looking, okay, we were designed for high efficiency. We were not looking at, so let's maybe shift some things from coal maybe to other energy sources, maybe gas or something different. Maybe optimizing a few things, maybe shutting down a few things. So the first part of the trajectory is fairly easy, all the way to here. And then it gets increasingly difficult, because then we need to start looking into those different assets. So what are the processes? What are the catalysts? What is the way to get that molecule to work that way? So this is where the really heavy lifting begins. And this is a point where we are going to really start to rework completely everything. So the company will have to be completely transformed. In 2040, none of our assets will look the way it looks today. And we're talking about hundreds of millions of euros of capex. That's going to be extremely difficult and expensive to do. But of course, it's going to need huge amounts of research. And that's maybe the little bridge to what we are talking about today. We already mentioned before that, yeah, there you are, that solving problems in a new way creates value, positions one well. So, and we have had success in past opportunities. Just a little bit to show that even a company as Lanxess that does not invest as much as others in research and development does focus on that and see great value in it. So we are, we've been lucky enough that one of our brome assets also contains lithium. So we're working on lithium extraction. So, and that, of course, with the fact that we have hydrofluoric acid within our assets and we have phosphorus, combining that, we can do LiPF6, which is one of the most important components in electric car batteries. So that's one thing we're working on. We have iron of certain qualities, or iron oxides, that can be used as precursors for these cathode materials also. So that might sound familiar. We're active very much in the area of biosecurity. So we have helped in the corona pandemic because we have certain disinfectants. We have support in the area of the bird flu or the swine flu, also delivering disinfectants to avoid, I mean, in some places, hundreds of thousands of animals had to be killed because there was, you know, a bird flu or swine flu occasion. And if we use these products, we can really protect the farms, protect the farmer subsistency, but also avoid killing all these animals. So that's the second one. And of course, the third one is we have both bromine, as well as phosphorus-based flame retardants. And flame retardants are extremely important. They keep our houses safe. They keep, you know, our families safe. So that's also something where, you know, a long tradition of research and development has basically kept us, you know, successful, which is good. I'll pause there for a second. So that was kind of like the general introduction, that I do need to do these plugs, otherwise my company doesn't let me come to these events. Now, coming maybe to the area of synchrotrons. I don't know who knows the company Honeywell. I worked at Honeywell, I worked at Momentive, I worked at Lanxess, at Bayer, and at Bayer Polymers. So it's 5 chemical companies over 20 years. And Honeywell has a division called UOP. It was formerly a separate company called United Oil Products. And what these guys do, it's very simple. They just like create processes for petrochemical industry. Sounds simple enough. And these guys are the absolute number one. They own basically 90% of all current petrochemical processes. Why? Because they've been working with Argonne National Laboratory since around the 1990s and really understanding these catalysts. So they've really worked out what is the structure-function correlation of catalysts. So not only do they have all these processes right now, when there's a new question from the oil industry and they want to do a new kind of process, these guys don't need to start like scattershot looking for things. They know already what kind of catalyst do I need because they have already deeply understood that through this work with Argonne National Laboratory. So they've got over 3,000 patents, a lot of processes in there, all the different catalysts. And the interesting thing here, so it's again to make a point my predecessors already made, science gives industry a significant competitive advantage. It gives us an edge. And of course, the second one, they've been working for 20, 30 years on this, so it doesn't fall out of the sky. Good corporations take time. Industry is not always patient, but we need to work on really taking that time, building that relationship, understanding mutually what our needs are to come here. And this is something that is really extremely successful. So maybe a little bit on the philosophical part. I was mentioning at the beginning the historic arc of chemical industry. And we used to have a lot of I started working at Bayer in central research. So it was 500 people, all looking at Horizon 3 and further, so like things that would be coming 5 or 10 years in the future. But that was in the 1990s and the early 2000s. In the past 20 years, more and more international competition, pressure for profitability has led major industry to really move away from long-term research to really tweaks and short-term application development and so it's become, this international competition has made it very difficult for large industry to keep large central research areas. Future inventions will only come from working together with academia because only you guys are really, have new tools, new approaches, new ideas, and then we need to sort of see, okay, what are the trends, what are the trajectories? That's part of my work, by the way, when I work at corporate development, is really determining, electromobility. I looked at that 6 years ago, 3D printing. So what is happening out there, and what do we need? And then we look at our own asset park, and we have the standard spectroscopy machines, maybe we have a couple of, but we don't have synchrotrons, and that's enormously expensive, I must say. But building a synchrotron isn't that cheap. So no industry will ever do that. So it's really, that's the point, really making sure that we have that cooperation. And of course, it's a mutual benefit because for academia, well, budgets are also tight for academia. So it's good if there is a possibility of getting third-party support through industry corporations. And for industry, well, we get access to very high or very advanced, very state-of-the-art machines without having to spend a lot of money, and of course to the talents, and that's also an important part. So you don't just need a machine, you need a pipeline of talents that you are continuously bringing up to speed and who know really well to work with these devices. And then, of course, we can mutually succeed. Now, of course, corporations don't always work the way everybody dreams about them, so we need to maybe, it gives us a chance to learn through the experiences. And I think, I've been on both sides of the equation, so both asking industry for the opportunity to help them. Back in my early days in what now today is called Airfield Microtechnic, but used to be the IMM, as well as in industry in several positions. So it's important really to look at things as a program. It's not a one project. So I come here and I say, oh, measure that. Oh, it doesn't work. I go away. We need to really build that long-term trust and partnership and really mutual understanding. What are my products? What kind of difficulties am I facing? And then, of course, the university says, okay, these are the machines I have. Maybe I can, maybe I need an engineer, maybe I need a chemist. So how to best sort of work together to have that match between the unmet need and the capabilities. So that's the first part, is really, it's a long-term commitment. The second one is, of course, and for both parties, make sure you choose your projects carefully. And the academia, and who said that? I think you said that it's important that really you have that discussion with the university and make sure they counsel you. They say, okay, well, let's do this kind of thing. And of course, if the science doesn't fit to the problem that I have, please say no quickly, then everybody is happier than if you try to finagle your way around it. So the academia has also a consulting responsibility vis-a-vis industry. Industry will say, okay, I have this big unmet question. Can your, synchrotron solve that? And then you need to be able to say, oh yeah, we can do this and this way, or we've never tried it before, but we have hope, or maybe you should try something else. Make sure that you're well prepared, because industry, my experience, again and again, there is this friction around, so who's going to own the IP? Who is going to earn what from the commercialization of the product? Who is going to, I think you will get the slides anyway, so. And of course, proximity matters. So it's not good to say, I mean, imagine I was, I don't know, in the States and I wanted to do a cooperation with you. So I come today, I give you a project, I come back in 3 years and I look at the project. That doesn't work. You need to have a closed feedback loop where you really make sure that you have, every 3 months, every 6 months, an exchange to make sure that what you are working on here in academia is fitting the problem that you are trying to solve in the industry, and the other way around, that industry is giving you all the information you need, that is giving you the background you need, is giving you maybe if you need more investment at a certain moment, that you don't dry out and wait for 6 months for the people. So you need to have those closed feedback loops to make sure that that works well. Kind of like, a few takeaways of what I think makes sense to think of before starting these things, and to make sure that your activities have a return on research. Yeah, so that was one arc. And I was mentioning at the beginning, Europe has a strong position economically and all that stuff due to all these industries that appeared in the early 20th century solving big problems. So that also means we're not working in a vacuum. There is also a geopolitical component here. So everybody is working, and every region and every major bloc is trying to develop these industry academia cooperations and to strengthen them. So we need to keep moving. Europe has let's say, a technological advantage. We have a leading edge, and we need to continue working diligently on that. Otherwise, there are other regions that will overtake us, and then we will just be buying technology from everybody else for the rest of our lives. I think it is incredibly impressive. So right now we are seeing the 20th National Congress of the Chinese Communist Party. So that's going on right now. And if you look at China, I mean, think about it. 70 years ago, they had a lower per capita earning as Colombia. I was born in Colombia. And now it's really the second largest economy in the world. So it's an incredible development. But it doesn't fall from the sky. They have been very, very focused. So they work very strategically on things. And if you look at that, they have been pushing universities in a very systematic way, making top universities. So they are now among the best 5 countries with the highest number of top universities, highest number of publications worldwide in 2017, very, very strong government support. And they have this common goal. So it's not just like, okay, it's haphazard. Luckily, some guy in industry stumbled over the website of somebody and said, oh, let's try. It's really driven and pushed by the government, making sure that industry and academia work together to develop society, to create the talents that you need to drive the advancement, strengthening industry, innovations, and really to make sure that that prosperity and growth take place. So that's very strategic. They are working on academia-industry cooperation with very strong focus. And of course, looking at those subjects that are relevant for autonomy, basically food supply, technology supply, that kind of thing. Okay, US has been, that has been going on forever, so they call themselves a knowledge economy. They still have the leading number of top universities, and there's always been this kind of like commercial drive behind things to say, okay, I have an idea, let's see how can I make a product or a service out of that. And of course, these partnerships, I mean, I was talking about proximity, a lot of companies really go close to those advanced learning centers, academic centers, to push that. So University of California, Stanford, and Silicon Valley, that is not accidentally that these things are very close together. If you look at the area around Boston, there are a lot, Procter & Gamble, Pfizer, there are a lot of companies in the medical industry that are close to Boston. That's also not an accident. But of course, in the US, there is a lot of focus on what's in it for me and how can I earn money. So there is always friction around, so who pays what at what moment in time? Does the university get rights on the commercialization of the product? And of course, having an idea in a lab, developing something, but then scaling it up, and so there might be 10 years between this and that, and the industry will say, so how is it fair that you help me here, and I have to carry all this risk? And so making sure that that works. So it's always very, very difficult to navigate that in the States. Partnerships are really hard work, and they've been working with new approaches, things like open source or whatever. Okay, that's the US. Japan, interestingly enough, has had a very, very long tradition. So they started really in the late 19th century, early 20th century, really pushing for academia to solve industrial problems. So they have this RIKEN, they have the Department of Engineering of the University of Tokyo, so really looking at industrial applications, and there was a RIKEN industrial group with really 63 companies which were spun off from academia. That was just before the Second World War. And after that, now they've really made universities are now national university agencies, so it's more easy for them to get monies from industry and to really sort of like do that kind of cooperation. So that's companies which really partner with those agencies have also shown higher profit rates, so that's also clearly very valuable. And they changed rules. Usually it was not possible for a professor in a Japanese university to own a company. Now they've changed that, and there are a lot of more, spin-offs and such things. Yes, maybe a second example. And yeah, I mean, Professor Hormus will chime in wherever my memory fails me. So I did mention we need to be patient, but we always get answers. And maybe it's not always the answer the industry wants, but, So we worked, I was at Momentive, the former GE Bayer Silicones, and I was responsible for research and development in the area of silicon-based elastomers. And of course, there's a big question. So elastomers are already something that is difficult to recycle or to reuse because, I mean, basically it's one big molecule. You can't grind it down and, like you could with the thermoplastic material. And basically, silicones are nearly indestructible. So you would, put that in a landfill and it would live for the next 10,000 years. So there was increasing drive to get those materials to be more biodegradable. And then we started thinking, well, I mean, there is thermodynamic value in a polymer, and bacteria have been on this planet for 3 billion years, and what they do is look at thermodynamic value and break it down. So there might be bacteria somewhere on this planet that are capable of digesting silicone elastomers. And we did a very systematic research with Professor Hormus and with the Hochschule Niederrhein, with Professor Prange. And yeah, after looking at all the bacterial strains, and we noticed that none of them wanted to eat our polymers, which is kind of sad. So on the one side, I was disappointed. On the other side, we knew that avenue was closed, and we could focus on other things. And right now, maybe just to sort of like reveal what the solution will be, we're thinking about more chemical thermolysis, that kind of process to break elastomers down. So difficult projects, that's what we're talking about. We're not talking about the easy things, those we can do in our own labs. The difficult projects will not always succeed, but we will always learn something and be able to clarify options and determine how to move forward with that. Good. So of course, how to prepare. And I think we've touched on that. I'm very happy that I, came in the last place and that Perry and Jordi spoke before me, because it's exactly what they were also mentioning. It's really, if you're going to work with an institution, this institution needs to have the highest level of expertise possible in that area. So make sure your equipment is the best equipment available, that your talent pipeline is well filled, make sure that you have personnel. So if an industry comes to you and says, okay, I need a project, you can't go like, oh, well, so we have November, so yeah, September of next year, new students will be coming, so maybe we can think about staffing it then. No, you need to have a pipeline of talent, so you can say, well, you know what? I have 2 people right now, and one is very good, and really being able to have that preparation. At Momentive Performance Materials, we made silicone elastomers for these high voltage isolation things. I don't know who knows that. I mean, back in the day, you used to have these big poles and the high voltage wires, and they were like these glass rings there. Do you remember those glass rings? Now, those glass rings became less popular because in the US, kids liked to shoot them, and then the city would lose electricity. You can make them also out of silicone elastomer. And then you need to make sure that they have very high breaking tension, that if they are wet, so if it rains on them, all the water must disappear. If they get dirty, so if they're there for 30 years and a lot of dust and grime and stuff comes on them, that they still are isolating sufficiently that if you've got 30,000 volts difference between the carrier and the cable, it doesn't creep across the polymer. So it's really, really challenging set of requirements. And we started looking for a university who could help us really measure that. And we looked around. We found TU Darmstadt. They have a Van de Graaff generator, which is like 10 stories tall. They had all kinds of fancy equipment. So we looked at that lab and said, so how do we start? How does industry begin? And I think we talked about that, I think with yours a little bit, but also you mentioned it too. How do you find the institution? And today, universities are found the same way as everybody else. Somebody in industry goes in the internet and goes to Google, high voltage, or synchrotron, and then we find a set of candidates, maybe look at how many papers they have, look at if they are active already with industry corporations, because that always gives us a good feeling. Okay, they've worked with industry before, so we don't have to teach them everything. And then we sort of like visit them and kick the tires on this. So what you say you have? Show me that apparatus. Okay, that's interesting. And really, we really try to identify who is the best academic institution to solve our problem. And of course, that's always a dialogue. So also the university needs to tell, you think you can solve that with this? No, it's going to work rather with that kind of thing. So really making sure that the institution has a high level of expertise is the best way to make sure, how do you generate the motivation, the appetite, make sure that your institution is top-notch, that it can be found on the internet, and then people will come and ask questions, and then be ready to field those questions well. The second part, so one part is the technology, making sure that you're really top-notch. The second one is prepare for a cooperation, because if you get there and the industry says, okay, so I have an NDA, and you go like, what's an NDA? Or if you go, so how are we going to work with IP? So you need to have thought through that before, maybe building a framework, trying to find out what is the best practice. Maybe having an in-house legal team. I mean, a lot of universities then retain external counsels, and then it's my legal department talks to some lawyer, and then he needs to talk to and then it takes forever to get that NDA signed, and then the contract takes even longer, and you go like, oh, this is... So make sure that that is quick and swift. And another thing that industry is increasingly interested in, there are a lot of funding programs out there. And of course, industry likes two things. They like making money. They also like saving money. So if the institution has some level of expertise in sort of like European or regional or whatever funding programs, and you say, oh, but you know what? If we set up this project in this way, maybe we can get this part of the project funded under, and then you only pay 50%. And the industry will also be happy. So kind of like three building blocks to make sure that the, at least the legal framework and the working conditions are well defined. Yeah, so I took that picture myself, so it's no copyright violation here. Yeah, so just to maybe look at the arc again, what have we covered? We spoke about industry, we spoke about how important industry has been in Europe. We've seen that industry has been always more under pressure to focus on the short-term application development and less on the long-term research and development. So it needs academia to do all that heavy lifting to retain that innovative edge, because we are also in a global competition for that. And of course, academia needs to prepare to be ready for those industry corporations by having the best level of technical expertise, but also the right kind of like legal framework to do that work together. So the future is bright for those who have prepared. Thank you.
Thank you very much, Harry, for your sharing your experience with industry and academia and synchrotrons. Okay. Any questions?
Harry, you mentioned that the Chinese, US, and others have a strategic plan how to, quote-unquote, move forward, and they have their unique capabilities. We in Europe have the Green Deal and, all the regulations driving it maybe, or not, hampering it. Is that enough to move forward? I mean, you mentioned LANXESS has the SDGs, your CEO was into it. Is this giving us enough momentum as Europe to compete with the others? Or what else is needed?
And that's a difficult question because I can answer with infinite gradations on that. So maybe let's start with a new Green Deal. I think it's a smart idea in view of the fact that Europe is facing a situation of, you know, sort of like competitive disadvantage from an energy point of view. Competitive disadvantage from the also population demographics. I mean, it's always less young people coming to the... So sort of like creating a walled ecosystem, pushing for a certain thing. So like saying, okay, we need to become green. And, you know, there's going to be a carbon border tax, and you're going to have to decarbonize, and we are... It's very smart the way the EU made that, because they said, they didn't sort of like mandate industry should decarbonize. They just like said, capital flows are incentivized to go to carbon reduced technologies. So of course, all companies that are in the stock exchange go like, holy cow, that means everybody's going to move away from unless I start moving. So it's good that there is this innovation happens under pressure. There is a big unmet need, there is pressure, innovation happens. That's good. Also giving Europe a chance, because those technologies are going to be more expensive. So sort of like having that walled garden approach of saying, well, if, I don't know, from India or from wherever the products come in and they're made with very CO2 emitting technologies, but very, very cheap, well, they have to pay for that carbon, you know, debt that they're generating before they enter the European market. So the European market is kind of like a bit secured around that. So that kind of like helps. So that's at least one equation where I have the impression the strategic levers have been thought through. Now you're asking, the question you were asking is bigger than that. The question was also, is that enough? And I think no one can beat the way China approaches things, of really having a very sort of, you have a 5-year plan, but you also have a 20-year plan, and you say, okay, I need these building blocks to be prosperous and successful. I am going to systematically start from the school level, or university level, or industry level, and make sure I get national champions aligned with top universities, aligned with, so that I get all the necessary. So this kind of like very strategic approach is something we can learn from. I think that's certainly, we could do more. I don't know if I answered your question or rambled.
I guess the one point I'm maybe curious about is the intrinsic motivation. We had this discussion yesterday, so if the beamline scientist is motivated by the topic, he or she puts in more effort. Mm-hmm. and you know, on a bigger scale is topics that are interesting and driven, say, by regulations and so on, can we make them even more attractive, so that what you say here is the bright future mm-hmm. is really sparkling, you know, that you're getting into it. So the question really is how we can excite ourselves to go this way and not just say, well, okay, that's a new kid in the block, I'll have to obey these rules and go by them.
I must say, we are fairly excited. At the beginning, we were kind of worried, saying, oh, what does it mean? But then we looked into it, and really that opportunity, that what I was showing maybe, you know, like 10 slides ago, with, okay, we need to decarbonize. And, you know, you think about that, and you say, oh, piece of cake. And then you can start looking at it and say, okay, well, this is easy, and this is easy. And then it gets increasingly difficult. And that's really exciting because we have committed to that. And we've committed, we were the first chemical company who committed to such an early carbon neutral goal without knowing how to get there. But that kind of like, you know, generates anticipation and excitement. How can we really achieve that? And again, we are very clear about the fact that 2025, we need to start those long-term research programs to get those new catalysts, those new processes. I don't know if it's going to be microreactors. I don't know if it's going to be a new generation of catalysts, but we need to change our complete asset park, you know, to turn that around. Yeah.
And I think that's really a motivation for the academic world. You know, that's an industry leading and having a basic understanding, or a need for basic understanding, where academia really can support.
Yep, agree.
It's more a comment than a question. China, the US, and Japan, it's one country. We have in Germany 16 strategic plans for decarbonizing, because we have 16 states in Germany. And also Europe, we have 28 or 29 or so. That makes life extremely complicated also. And finding a solution there, to speak with one voice and have one rule, and not laws in 5 different official languages also, that's a challenge. Therefore, that comparison with China and the US is right, but it's extremely difficult for Europe. It's even extremely difficult for Germany also.
Agree, and we need to solve it. And we need to solve it. I think that's one of the big issues that the European Union has. This unanimity principle is killing us. We need to be able to work on a majority-based rule, so that needs to be changed. And also, Germany needs certain policies. It would make a lot of sense if they were homogeneous. Federal systems are very good, but we need to homogenize certain things so that we are more capable and better ready for the future. Otherwise, we'll be run over. Yeah, sorry about that.
Yes, the last. Any other question? Just the last question. Bringing the topic to my interest. What do you think that the synchrotron, do you think that the synchrotron can help to those challenges?
And I would do the arc to the first industrial example that I had, which is basically Argonne National Laboratory. So really being able to develop, to have a very deep understanding of this catalyst function structure, relationship, will help us a lot because we have literally hundreds of chemical processes that we need to change, to turn around. We have a Verbund set up in Leverkusen where really a lot of assets really are interconnected and we need certain types of waste streams to be able to get the interest for so we need to get that moving. The current speed of development of catalysts is not sufficient for what we are going to attempt over the next 20 years. And that's where we will certainly need support from a synchronous radiation lab.